and welcome to FusionEPtalks, a student-led webinar platform for sharing knowledge about nuclear fusion science and engineering. I'm Ekaterina, and I would like to introduce our speaker today, Jędrzej Walkowiak, who will be speaking about calculations in plasma physics and how to balance their accuracy and speed. Jędrzej graduated from the Poznan University of Technology. He first completed an engineering bachelor course in the field of energy engineering, and then he completed his master's degree in mechanical engineering in the same university. After 2 years of working in the automotive industry as a CFD engineer, he started his PhD at the Institute of Nuclear Physics, Polish Academy of Sciences in Krakow. He works in the interaction of fast electrons with plasma impurities in tokamaks and developing dedicated models for plasma simulation codes. So without further delay, I give the floor to our speaker today.
Thank you. Welcome everyone. Today I will have a pleasure to tell you about a bit of my work on the calculation in plasma physics. I have a bit unconventional field in the plasma calculation because I don't focus on the accuracy of my models. I focus on the computational speed of my models. And to give you some introduction to the topic, the plasma physics is a very complicated field because plasma in general is an ionized gas. And because of this ionization, it interacts with the electromagnetic field, and by interaction it means that it not only responds to the magnetic field, it also takes part in the creation and shaping of this magnetic field by its own. And on the top of that, the particles in plasma are charged, which means that they can be affected by Lorentz force and other phenomena which cause the particle drifts, which is an effect which cannot be really well represented in the typical fluid model. So if we would like to make a simulation of plasma, we cannot just take the simplest approach of representing all the forces or all the particles, because we have too many particles in plasma which we want to simulate. We have a problem of the wide range of the spatial and temporal scales, because if we would like to make the simulation which include the smallest time scales or the spatial scales, it would mean that it would be extended to the enormous scales to catch the longest or largest effects which occur in plasmas. We have also variety of nonlinear interactions, many modes of oscillation inside the plasma. All these things make the simulations really complicated. That's why during the simulation, we usually replace part of the simulation by models. By models, I mean the functions or functionals, which basing on some input parameters are able to give us output, which replaces parts of the simulation. Reduce the complexity of the plasma experiments. We are able to represents all interesting parameters as a functions, simple functions of times. So we can reduce all our simulation to some simple models, which will give us the values of interest. Example of such approach is the Metis software. Metis is a software based on the Chronos code. The main difference is that Metis replaced many of the first principle or ab initio models from Chronos with 1D or 2D simplified versions of these models, and it still gives quite similar results in the term that it can give you the trends and some values of the plasma parameters. Here, for example, you can see the values of the currents calculated with Metis and in Chronos. The main difference is that Metis calculates the results about 10,000 times faster than Chronos, which basically means that, for example, if you want to calculate the discharge, this one is for ITER, which took 1,000 seconds. With Metis, we are able to make it in about a minute. In case of Chronos, it can take days to get the results of the single discharge. This gives us first the benefit of being able to analyze much more data than with the more detailed code, and it gives us some other benefit, which I will discuss later, because it can be used in iterative calculation. And now I would like to give an example of the Fokker-Planck equation solving, which was part of my work from the last year, realized as part of my PhD. And Fokker-Planck calculation is important part of many calculation codes. In this case, I use it as a part of the chain of codes, which is used for the calculation of lower hybrid current drive waves, propagation, and deposition in plasma. Here you can see that we used many codes to get the UR results. What is quite important is that the results from the Fokker-Planck equation solver can be used as an input for Metis. So we are able to run this suite of codes in an iterative way, improving the input parameters for Metis in each loop and getting more accurate results this way. And now to the Fokker-Planck equation. Fokker-Planck equation describes the evolution of plasma in a kinetic model, and it consists of three important parts. First, describe the elastic collisions, and the main parameter here is the deflection frequency. The second part describes the inelastic collisions and is defined by the slowing down frequency. And the last part is about parallel diffusion part of the equation. And in my work, I will focus on the elastic in an elastic collision, because I was trying to implement the effects of partial screening into this collision frequencies. I will give the example on the elastic collision because this is the easier case to explain. The physical explanation of the partial screening is that normally when we have the electron which is passing closely to some ion, it will be deflected because of the Coulomb interaction between the electron and the nucleus. So the nucleus is deflecting the trajectory of the electron, but the nucleus is shielded by some bound electrons, which reduce the total charge of the nucleus, which is seen by the passing electron. And now, if the passing electron is fast enough, it will penetrate through the cloud of bound electrons, and it will be not shielded by all of the electrons bound to the nucleus, but only by part of them. And this is the situation which we call partial screening. And here we can see the equation for the collision cross section. Here, which I will focus on, is the nucleus charge reduced by the atomic form factor. This atomic form factor defines how much electrons take part in shielding of the nucleus during the collision. This atomic form factor can be calculated from the electron density around the nucleus. We have a few approaches for calculating electron density. One of the most accurate I use is the density functional theory based approach. This is ab initio model, which takes into account many quantum mechanical properties of the atom. The main problem with this approach is it is quite time consuming and it needs numerical integration of the resulting electron density to obtain the atomic form factor. An alternative is the Thomas Fermi based approach. Thomas Fermi model is quite old model. It is semi-empirical model. It doesn't even reproduce the electron shell structure of the atom, but it is able to calculate faster. But still, in the basic Thomas Fermi model, we have the problem of integration the electron density to get the atomic form factor. We are not able to calculate it in the analytic way. We must to make the numerical integration similar as in the case of the density functional theorem. But we have the Kirillov approximation of the Thomas Fermi model, which gives us very simple solution, analytical solution to this integral. And we are able to calculate it 1000 times faster than with the numerical integration of the DFT approach. Here we can see the example of results for the simple tungsten ion which is only single ionized. And here with the blue line, you can see the results for the density functional theory model, and cyan line represents the results based on the Kirillov approximation of Thomas Fermi model. As you can see, it's not as accurate as, for example, the numerical integration of the Thomas Fermi model, which is represented in the red line, but it still represents the shape of the function quite well. And if we would like to calculate the collision frequency ratio, we will get quite reasonable representation of the collision frequency. As a word of explanation, the collision frequency ratio is the ratio of the collision frequency calculated with partial screening and without partial screening. So in this case, if we include the partial screening effect, we can see that the collision frequency will be few times higher than without including the partial screening. So it is quite important phenomenon. The importance of this effect depends on the level of ionization of the given ion and on the momentum of the colliding electron. And as I mentioned, as you can see, in case of the Kirillov approximation, it is less accurate than the direct the ab initio models on the direct integration of the Thomas Fermi model. But because it can be calculated much faster, it is worth to lose some accuracy and to use this model, because then we can, for example, use it in the iterative way to improve the initial parameters we use to obtain for our solution. I would also like to comment highest level of the fast computation, which is a real-time computation. It gives us strong benefits. Apart from being able to calculate more data in the same time, with the real-time calculation, we can use the results from some diagnostics as a feedback to the control system of the tokamak. So we are able to better react on the phenomena which occur in the plasma, and our control system is able to contain plasma longer and with smaller losses. And here you can see the example of the plasma tomography of the soft X-ray diagnostic system from STOR Supra, where we would like to obtain the cross reconstruction of the emissivity inside the plasma cross section, basing on the readings from two cameras, one vertical and one horizontal, with quite limited number of channels. It's quite complicated problems because it's so-called ill-posed problems. It's not easy to calculate it fast in a conventional method, but we can use the neural networks in this case. Neural networks in general are based on the connection of many neurons, which are simple mathematical entities which collect few inputs values, weight them, and process them by some simple internal function to process the output. And by connecting them into the network, we are in general able to solve almost any function. So in our case, we would need to take the readings from the channels of the cameras as an input. Then we will place some so-called hidden layers, which are used for processing the data. And as the output, we will get the 2D emissivity field of the plasma inside our tokamak. What is important is that in case of neural networks, we don't have to set all the weights of the inputs to the neurons and all the parameters of the functions inside the neurons by hand. We can use the training for this. So we should provide this neural network with pre-calculated data of input and output, and it will learn on it to produce the similar results from the input which wasn't used in the training. And here we can see the simple example of the reconstruction of this emissivity in case of the torus-supra soft X-ray diagnostics. I made simple neural networks with 2 hidden layers with 40 neurons each, so it's quite small neural network, and trained it with something about 2,500 examples of the original images and reconstructed images. And here you can see the reconstruction of the original image, which was artificially created. The neural network didn't see it during the training, and it was able to produce more or less reasonable reconstruction of the original image, basing on the readings from the camera as it would look like in the torus-supra tokamak. It's not perfect, but the neural network I used is very simple. Now there is work on the creating of the much more refined neural network, which should be able to predict the emissivity profiles in more detailed ways. And as you can see, the potential of this method is quite interesting. And of course, the possibility of applications of neural networks is much wider than just inverse problems in tomography. We can use it in plasma modeling to replace some complicated model with neural networks. We can use it for pattern recognitions like disruption predictions or edge localized modes predictions. And there is an example from the W7X stellaratron to process the images from the infrared cameras to support the control systems of the machine. So in general, the neural networks are very fast in computing the results. The most time-consuming part is designing the neural network and training it with predefined examples. This is one of the problems that we need to first have the set of solved cases to use it as a training for our neural network. This limits us, but in general, the neural networks are a very interesting topic, and especially in case of making the computation in a fast ways, it is worth to think about them. Okay, and to somehow sum it up, I would like to give you some take-home messages. So first, that despite the fact that plasma physics is very complicated, we can use some dedicated tools to solve our problems. And this way we can deal with many different phenomena in the tokamaks. But sometimes it's better to give up some accuracy of your model to make it faster, because apart from the fact that it is usually more useful if you can make the simulation in a shorter time, it is also good because you can, for example, use it in the iterative approach, or you can use more models at the same time, which will reflect more phenomena in plasma and give you more accurate result than just tuning up some basic first principle model. And in these cases, the using of semi-empirical or pre-calculated data can be very, very useful, and it's often more useful in the computation than focusing on some ab initio or first principle model, which are more elastic, but this elasticity is often not worth it. So you need to know what you want to achieve. And it's worth to know that something like neural network exists. It opens possibility to solve so many problems with great speed that I think it should be obligatory to almost all physicists to learn at least the basics of it, to know what are the possibilities of these methods. And this is everything from my side. Thank you very much for your attention. And if you have any questions, I will be happy to answer them.
Thank you very much for a very nice overview about calculations in plasma physics. It's always good to learn how to balance possibilities that you have and speed and accuracy of your calculations. And in each case, I think many scientists, they face these questions. So now the floor is open to questions. And to do so, please raise your hand. You can find raise hand option in the bottom of your screen under reactions button. But if you have any issues with that, you can drop your question in the chat or let me know that you have a question. But I already see raised hands. Amir, please go ahead.
Yes, hello. Thank you for this opportunity and for a wonderful presentation. I have a question regarding the simulation of turbulence. While I did some investigation, I couldn't find that there are any specific turbulence models in the CFD of plasma physics, like in regular CFD where you have a K epsilon, K omega, or so. Do you have any experience with any models that that are included in the plasma physics simulation? Thank you.
Thank you for this question. Unfortunately, I'm not really involved in the simulation with the turbulence models. I focus more on the field of the more basic interactions, like on the atomic level of the plasma. I know that there are some, I think that I meet some solutions, for example, with neural networks to plasma modeling, but in general, the turbulences in the plasma is much more complicated than in the simple CFD model. Because in the CFD, it's based on the empirical models mostly. And in case of plasma, first, we have much smaller base of empirical data. And the second is that we have much more phenomena inside plasma, like the drifts, the issues with the fact that the particles are rotating along the magnetic field lines and similar cases. So unfortunately, I'm not able to answer your question directly, but yeah, I can only comment it that way.
Okay, thank you. Any other questions? I don't see any raised hands for now, so I'll maybe ask myself a more general question. What are your future plans for your PhD? What topic are you planning to focus on now?
Basically, what I am working on now is related to the inelastic collisions in plasma, and more specific on the mean excitation energy. So the energy which is in average transmitted to the ions by excitation of the bound electrons during the collisions of the free electrons with the ions. It's quite a complicated topic, and when I will deal with this, I will spend some time on introducing these models into the software from this chain of codes I mentioned. So in my case, it will be the Look software, and I will be making the statistical analysis on the database from the West tokamak on the experimental data to check the influence of various parameters on the on the plasma. For example, my colleague from the project I am working on was working on the Bremsstrahlung emission from the plasma when including the partial screening effect. And it came out that when you include the partial screening effect, the Bremsstrahlung emission can be changed by the factor of 2, for example, in some cases. So we found out that this physical phenomena can be important. It's not always the case because it's mostly happens when we have heavy impurities with like tungsten, which have a high atomic number, and it's almost never fully ionized in plasma. And we need usually fast electrons. So in case of tokamaks, it usually means runaway electrons or the electrons from the lower hybrid current drive, because they are accelerated to quite high energies on the order of few hundreds of kiloelectronvolts. So they are also interacting in a bit different way than usual electrons in the plasma. And we are taking these phenomena into account, and I hope that I will find out when it is important, when it's not, and be able to define some restrictions on the current drive methods.
Well, I wish you success in this challenging topic. And I saw raised hands from Francis. Am I right?
Yes, yes, yeah. So I have a question. Like, I would like to know more about this Metis. Like, I read in one of the papers that this is like a 1.5D model, but I don't quite get what exactly they mean by saying that Metis is a 1.5D model. Like, do you know what exactly that is?
I'm not sure, because Metis in fact is including a few models, and some of them, I think that when they write about 1.5D model, it basically is related to the fact that it's 1D model in the closed in the toroidal loop. So it's not 1D model from definition, but it's not also the 2D model, and that's why they use the 1.5D model. It's related to the fact that you have the 1D model closed in the loop, or like to simplify this.
Okay, yeah. So
yes,
yeah, it was quite confusing for me. Yeah, thanks for doing that. Yeah.